Chemical engineering is a fascinating field that shapes our world in countless ways. From the medicines we rely on to the materials that build our homes, chemical engineers are constantly innovating and improving our lives. To understand this complex field, we must first grasp its fundamental language, the key terms that underpin its principles and practices. In this exploration, we'll delve into the world of chemical engineering by dissecting some of its most important concepts. We'll break down complex ideas into digestible pieces, using everyday analogies to illuminate their significance. Imagine a world without plastics, paints, or even soap. These everyday items and countless others owe their existence to the principles of chemical engineering. By understanding terms like polymers, viscosity, and solvents, we gain a deeper appreciation for the intricate processes that transform raw materials into products we rely on daily. Whether you're a student just beginning your journey into the world of atoms and molecules, or a seasoned professional seeking a refresher, this exploration will equip you with the knowledge to navigate the fascinating language of chemical engineering. Join me as we embark on this journey of discovery, unraveling the mysteries behind polymers, viscosity, solvents, and more. Together, we'll unlock the secrets of these key terms, exploring their practical applications and appreciating their profound impact on our daily lives. Our exploration will not only enhance our understanding of chemical engineering, but also ignite a sense of wonder for the intricate processes that shape our world. So, fasten your seatbelts and prepare for a thrilling ride through the fascinating world of chemical engineering. Let's dive in and decipher the language that governs the transformation of matter, the creation of new materials, and the advancement of human progress. Polymers are the unsung heroes of the material world. These long chains of repeating molecular units, like tiny Lego blocks linked together, form the basis for a vast array of products we use every day. From the plastic bottles we recycle to the rubber tires on our cars, polymers are essential to modern life. Understanding their properties and behavior is crucial for chemical engineers seeking to design and develop new materials with specific characteristics. Imagine a string of pearls, each pearl representing a small molecule. When these molecules link together, they form a long chain, much like the string of pearls. This chain is what we call a polymer. The properties of a polymer depend on the type of molecules in the chain and how they are arranged. Just as different types of pearls create unique necklaces, different monomers result in polymers with distinct characteristics. For example, polyethylene, a common polymer used in plastic bags and bottles, is made up of repeating units of ethylene. Its flexibility and durability make it ideal for these applications. On the other hand, polystyrene, used in disposable cups and packaging materials, is more rigid and brittle due to the presence of a bulky benzene ring in its repeating unit. These examples illustrate how the structure of a polymer dictates its properties and ultimately its applications. Chemical engineers manipulate the structure and composition of polymers to create materials with specific characteristics tailored to their intended use. By controlling factors like chain length, branching, and cross-linking, they can fine-tune the properties of polymers to meet specific demands. This ability to tailor polymers has revolutionized industries ranging from packaging and construction to medicine and electronics. Viscosity, simply put, is the resistance of a fluid to flow. Think of honey slowly drizzling off a spoon compared to water splashing quickly from a glass. Honey has a higher viscosity than water, meaning it resists flow more strongly. In chemical engineering, understanding viscosity is crucial for designing processes involving fluid flow, mixing, and transport. Imagine trying to pump thick molasses through a narrow pipe. The high viscosity of molasses would create significant resistance, requiring a powerful pump and potentially slowing down the entire process. Chemical engineers carefully consider the viscosity of fluids when designing pipelines, reactors, and other equipment to ensure efficient operation. Viscosity plays a critical role in various chemical engineering applications. For instance, in the production of paints and coatings, viscosity determines how easily the paint can be applied and how well it levels to form a smooth finish. Similarly, in the food industry, the viscosity of sauces, syrups, and other liquid products affects their texture, pourability, and overall sensory experience. Controlling viscosity is often crucial for achieving desired product properties and process efficiency. Chemical engineers use various techniques to modify viscosity, such as adjusting temperature, adding solvents, or incorporating thickening agents. By carefully manipulating viscosity, they can optimize processes and create products with specific flow characteristics tailored to their intended applications. Solvents are the chameleons of the chemical world, dissolving other substances to create solutions. Think of sugar dissolving in water to make a sweet drink. In this case, water acts as the solvent, breaking down the sugar crystals into individual molecules dispersed throughout the solution. Solvents are essential tools in chemical engineering, facilitating reactions, separations, and the creation of countless products. Imagine trying to clean a greasy pan without soap. The grease, being hydrophobic, water-fearing, wouldn't mix with water alone. However, adding soap, which contains surfactants, allows the grease to dissolve and be washed away. Solvents play a similar role in chemical processes, dissolving reactants, facilitating reactions, and enabling the separation of desired products. In the pharmaceutical industry, solvents are crucial for extracting and purifying active ingredients from plants or chemical synthesis. Similarly, in the manufacturing of paints, inks, and coatings, solvents dissolve pigments and binders, creating a homogeneous mixture that can be applied to surfaces. The choice of solvent depends on factors like the solubility of the target substance, the desired concentration, and the environmental impact. Chemical engineers carefully select solvents based on their specific properties and the requirements of the process. They also consider factors like toxicity, flammability, and environmental impact when choosing and handling solvents. As responsible stewards of the environment, chemical engineers are constantly seeking greener alternatives to traditional solvents, minimizing waste and reducing the ecological footprint of chemical processes.